Mic test 1 2 3. Mic test 1 2 3. Okay, so let us begin. Hopefully this will be a very short stream. So the question here is given a triangle array, return the minimum path sum from top to bottom. For each step, you may move to an adjacent number of the row below. More formally, if you have an index I on the current row, you may move to either index I or index I plus 1 on the next row. Okay, so our job is to return the minimum path sum from top to bottom. Okay, so for this I have tried to use Excalidraw, just with the intention of being able to explain the problem a little better, even though I don't have much experience with this site. So yeah, this is what the question states. You have this kind of two-dimensional array, and each row is a row of a triangle, right? So the first row contains one element, the second row contains okay, this is not correct. It should actually be like this, right? This is actually a triangle. So as you can see on the ith row, that is the 0th row, there is one element. On the first row there are two elements, on the second row there are three elements, and on the third row there are four elements, right? So our job is to figure out the minimum cost in order to reach from this starting point, that is 1, to either of these, right? 9, 10, 11 and 12. So I can go from 1 to 3, from 3 to 6, from 6 to 11, or I can go from 1 to 3, 3 to 6, 6 to 11, or I can go 1 to 3, 3 to 6, 6 to 10. So the only direction that we can move in, suppose we're in this row, right, and we are at 1, so we can either move down or we can either move to the right diagonal, right? So 1 to 2 or 1 to 3. Similarly, when we are at 3, we can move either from 3 to 6 or 3 to 7. We cannot move 3 to 5. Those are the rules. So whenever we think of the minimum cost or the shortest path, right, we tend to think that it can be solved with Dijkstra, but in this case we only have two directions that we can move in, right? Either down or the right diagonal, right? And it can be solved by using Dijkstra, but the time complexity would be E log V. So E in this case, since this is a grid, would be where each cell is a node, right? So E would be m into n, and even the V, right, the vertices, that would be m into n. So the total time complexity would be m into n log m into n. So that's an extra log factor, right? So that is why we tend to look towards the dynamic programming solution to see if it can give us something better, right? So what we can do is we can start from 1, right? we can start from 1 and then we can go either of the two paths. Suppose we are in 2, we can go either to 5 or we can go to 6. So we have to try all the ways, right, in order to find out which is the minimum path. So whenever we think of going to all the paths, we think of recursion. So that's what we're going to do. So initially what I can do is I'll just write the function. Let me maximize this, right? Okay. So we have public and let's say f, and since we are working on a grid, we have to use two indexes, that is int I and int j, right? We would also need to carry the list, right? List of integer, that's like a two-dimensional array. Triangle, and let me go back here. So we start from here, right? So we need to think of a base case for the recursion. When does the recursion stop? So when we start from here, we can move here or here and then here, right? So as soon as we reach the nth row, right, that's when we stop. It can be anywhere. We can reach 9, we can reach 10, we can reach 11, or we can reach 12. So if we reach either of these states, then we stop, right? We can also do it in the reverse way, right? We can start from 9 and then go to 6 and then go to 3 and then go to 1, right? But if we do that, then we would have 4 starting points, right? We would again have to start from 10 and then figure out where we can go. So instead of that, we will just start from 1 to make things simpler, because that allows us to have one starting point. So what we do is, whenever we reach the let me increase the zoom a bit, right? Someone had pointed out earlier that it's a little too small. Yeah, I hope this is fine. Now if we have reached the nth row, right? So if I equals to n minus 1, right? Let me just, since we are not passing the value of n, we can calculate it here. It's not a big deal. And equals to triangle dot size, right? So whenever we have reached the nth row, right, we can simply return the element, which would be triangle dot get, that would be the n minus 1 or ith row in this case. Okay, that would give us we would also need the element, right? So it would be j, element in that column, so it would be j. So once we do this, I think this is the base case. Let's think of an edge case, right? Can we go out of bounds, right? Like suppose I'm at 1, the only two directions I can go is either down or right? I can't go left, so I don't need to put a condition wherein we can go out of bounds from the grid, right? Because I can't go left from 1, I can only go down and I can only go right, and those will always be valid cells, right? From here I can go down and left, right? From here down and left, and from here, like from 10, I don't need to go down or left, because as soon as we reach 10, we just store that value, right? That's the base case. So what we do is, now we just calculate the values, right? So we can go either of two directions, that is, we can go down. So if you are going down, right, if you're going down, like from 1 you're going down, right, so you need to store this value of 1, right? 1 plus depending on the path will be depending on the path of the recursion, we'll get the values, right? So we need to store this value for first, right? So we need to add 1 plus whatever the recursion, whatever the path the recursion is taking. So 1 plus this path, or 1 plus this path, right? 1 plus the down path, or 1 plus the diagonal path. So the down path is, we need to take the actual value first, triangle that get I dot get j. So the moment we get that, and then we use recursion to find the value of the rest of the path. So that would be, since we're going down, right, we're going down, so it has to be I plus 1 and j, right? And diagonal, I'm going to use a very famous variable name dg to signify diagonal, and it would be the same element dot get j, right, plus the recursion, right? It's we are going to diagonal, right? So it has to be I plus 1 j plus 1, I plus 1 j plus 1. We are also carrying the list, by the way, so we need to mention that as well. Triangle, right? And then what do we need, right? So suppose I went through this path, right? 1, 2, 5 and 9, right? And then the other path that I went was 1, 2, 6 and 10. So what do we need out of these two paths? We need the minimum, right? So we store the minimum from the downward path and the diagonal path that we start off with. So we just return the minimum of either the down path or the diagonal path, right? Yep. So we can just call the function here. We need to pass ing, right? So ing will be 0, and we need to pass the triangle. So I think this should be okay for the recursive solution. Let's run this and see if we've made some mistakes. Yeah, this is running perfectly. But then if I try to submit this, it would give you a TLE, right? Time limit exceeded. So we need to memoize this solution. So what we can do is I'll just try to show you why memoization works, right? So what I can do is, let me just start here, right? We start with f of 0, 0, right? And then we can either go down or we can go to the diagonal, right? So if you go down, it would be I plus 1 j, right? And if you go to the diagonal part, it must be I plus 1 j plus 1, that is f 1, 1, right? Similarly, from f of 1, 0, I can either go down, right? If I go down, it would mean 2, 0, right? And if I go diagonal, sorry, it would be I plus 1 j plus 1, that is 2, 1, right? So let me draw this properly so you can understand. So yeah, this is how the recursion works, right? It is so difficult to use with the trackpad. I think I have to use my mouse if it's possible. Let's see, yeah. Okay, so this is fine. Yeah, I think this would help us understand it better, right? So there are two directions, right? You can either go down or you can go diagonal, right? So even for this we can go down or diagonal. Even for this we'll be able to go down or diagonal. Let me just use this. What I can do is I'll just copy this and yeah, so I can go down. If I go down, it would be I plus 1j, right? And if I go towards the diagonal path, it would be I plus 1j plus 1, that is 2 comma 2. So you can see this, right? In the recursion, this is the recursion tree, by the way, so you can see that there are overlapping sub problems, right? So this is how recursion works, right? You start from here, go towards the left, and then you go towards the left, and then you come back, and then you go towards the right, and then you go back again here, and then you go to the right, and then you go to the left, right? So when we reach here at this point, we don't have to go through this recursion process again, right? 2 of 1 will call something on the right, on the left, and something on the right? We don't need to go through that path because that path would have been already calculated here, right? So that is why we can use we can store this value actually, so that when the recursion reaches this point again, we can just use this value that we have stored here, right? So that's what I'm going to do. I will just declare a DP array, right? DP equals to, okay, we need to calculate the size of the grid, so that would be triangle dot size. Okay, new int n cross n. I mean, we wouldn't need n cross n, but then just for safety reasons, right? And then we also need to, well, this is Leetcode, so we can actually declare all of it to -1. We can use the arrays.fill method, right? And what it would do is it would fill every row of this array with -1. And then what we can do is we can just pass this walking helmet. We can pass this TP here, and then we can just store this value instead of just returning. DP of I j equals to, and then here we can just mention, right, if this value already exists, then we can just return it. We don't need to call further recursion. If dp of I not equals to minus 1, and we can just return dp of ij. And then we also need to pass the dp here. I think this should work. Let's try and compile this. Yeah, it's working absolutely fine. Let's try to submit this. Yeah, this is also giving us TLE. So what we can do is we can move towards the tabulation solution. So for tabulation, we don't need to initialize it to -1. So in tabulation, what we do is we try to convert whatever base case we had here, right, in the memoization solution. We try to convert this into tabulation. So in memoization, what we were doing is we were starting from here, right, and then we were going here, and then we were going here, and then if this was the last row, right, if this was the last row, we take this value, we come back, and then recursion comes back from here, and then again from this path, when recursion is over, right, it comes back here. So we take the minimum of either of these two, and that's how we compute the value of f of 0, 0. But in tabulation, it's just the reverse, right? We have to start from the bottom, right, from the base case. So that's what we're going to do. So if we have reached the nth row, right, so we can just take that value, right? Like suppose if we have reached 9, then we just take that value. If we've reached 10, we just take that value. If we reach 11, we take 11. If we've reached 12, then we take 12, right? And from here again, that's how the table is filled actually. So we have all these values initially, and then from here we can either go up or we can either go right, diagonal, since it's the reverse. So what I can do is, for it has to go to n, right, and j equals to 0, j less than n, j plus plus. So our dp of n minus 1, right, n minus 1 and the particular column would be that exact value. It would be n minus 1 dot get j. So this would take care of a base case, and then we start with the for loop for tabulation, right? So let me come back here. As you can see, we need to think, right, what are the possible values of I and j. So it can be 0, 1, 2, 3, 4, 5, 6, 7, 8 till n, and then this one, when it comes to the second parameter, right, second index, right, so how far can it go, right? When it comes to I, we know, right, it'll go 0, 1, 2, 3, right, because there are these many rows, but the column might not actually go till n, right? As you can see, there are 2 elements here, there are only 3, there are only 4, there is only 1, right? So on the 0th row, that is ith row, there is 1 element, right? And let's say in the 3rd row, where I is equal to 2, so the index goes from 0, 1 and 2, right? So in tabulation, we are filling the table in reverse, right? So we're actually filling this value and this value, then this value, then this value, then this value, then this, and eventually when we reach here, we will have the same value that we would have had in recursion, right? F of 0 0. So f of 0 0 signifies the minimum path that we can take if we start from the starting point 0 0 and reach any of the nth rows, right? So that's what we're going to do. Or since in the base case we have already filled the n minus 1th row, we're going to start with n minus 2, right? I equals to n minus 2, and I is greater than equals to 0 because it goes till 0. I minus minus. In case you're not understanding what I'm saying, that's okay, because I don't think I have a lot of experience explaining dynamic programming solutions to anyone. So I understand there are a lot of basics that you need to understand before you dive into these things, but hopefully it is helping someone at least, right? Then we go for the jth loop. So like I said, right, what could be the values of j? So if we start from the reverse, that is suppose from 12, right? And this is the, let's say, I equals 0, 0th row, 1st row, 2nd row, 3rd row, and this is the 2nd row, right? If this is the 2nd row, then we would start from this thing, right? The column value will be 2, then it would be 1, then it would be 0. So we would start with I, right, in reverse. And j has to be greater than equals to 0, j minus minus. Once we've done that, right? Once we have done that, all we need to do is we just need to copy this logic, right? This logic here. That's the same thing. We can either move down or we can move to diagonal, right? And instead of f, we can just write the value that we calculated in the table, right? So we're moving down, it should be I plus 1 j, and if we are moving diagonally, it should be I plus 1 j plus 1, right? Once we're done with this, we just need to store the value, right? So dp of I j would be math dot min of, we're just taking the minimum value of these two parts, so down in dg. Once we are done with that, like I said, when we started with the recursion, right, we started from f of 0 0, and then we moved down, and then back up here, and then again we went to this path, right? After we traversed this entire path, we had the value of f of 1 0 and f of 1 1, and whichever was the minimum, we took it into f of 0 0. So f of 0 0 actually signified the minimum path, right? Minimum cost that it takes to go from 0 to any of the last rows, right? So f of 0 0 will actually hold the final values, but in this case we're storing it in a table, right? So it would be dp of 0 0. I think this should work. Yeah, it is compiling. Let's try and submit it. Before we were getting a time limit exceeded, but hopefully this gives us the right answer. Yes, so it is working. Now the time complexity, right, of this problem, right, time complexity of this problem would be big O of m into n, right? N into n actually, because we are using DP array size of n into n, and the space complexity would be, again, it's n into n because let me just explain it if you didn't understand. It's n into n because we're using these two loops, right? But it won't exactly be n into n, right? Because even though we're going through n rows, right, it doesn't have n columns. This one has 1, this one has 2 columns, this one has 3 columns, this one has 4 columns. So it's not exactly n into n, it would be lesser than that, but this is the time complexity that we can write, and the space complexity would obviously be n into n because we are using a DP array of size n into n, right? So how do we reduce this size, right? Can we reduce this size? Can we reduce the space complexity? The answer is yes. And why is it yes? That's because when you look at this line, right, we're using dp of I plus 1j and dp of I plus 1j plus 1. So we're actually using, since we're filling the table in reverse, right? Can we make a table here? Okay, I'll just make a rectangle to show you. So I'll just draw a simple table, right? Here. So we're actually starting from here, right? We're actually starting from here, filling the table from here, then this value, then this value, then this value, then this, then this, then this, then this, right? So the moment we're here, right, let's say it's anything, it's just x, if this value is also x, I'll just make do with circles, man, because I don't know how to use this. Okay, so when we are here, right, in order to calculate the value of this, we need not this, sorry. So yeah, when we are here, right, in order to calculate the value of this, I would either need the I plus 1th value or I plus 1j plus 1 value, right? So instead of storing the entire grid, right, that is n into n matrix, right, what we can do is we can just store the previous row or the next row, right? So once this row is filled, right, we can use this row to calculate the values for this row. Again, once this row is filled, we can use this row's value to calculate the value for this row. So at any moment we just need 2 rows, right? We don't need the entire grid. So that's what I'm going to do. So instead of dp n into n, what I'm going to do is I will just declare a single array and I'll just name it as next, right? Single array, and then instead of n minus 1, I'll just do this, right? So next will actually hold the this last row's values, since as the base case, right, it would actually hold 9, 10, 11 and 12, and we can use these values to calculate the value of this row, and this row, right? I mean, we can actually use 9, 10, 11, 12 to calculate the value in this cell, and this cell. So that's what I'm going to do. Now that I have my next array, I can use a current array, right? We need to store, like, whenever we are here, right, in this row, we need to calculate this value, and this value, right? So we need some kind of an array to store these values, right? We are calculating these values with the help of this next row, right? That's what I'm using. The next row's values I'm storing in this array, and we're also calculating the value of this current row, right, using this next value. So this current row also we need to store it, so that when we reach in the first row, like in this case the first row, this current row, right, would become the next for this row. So that's what I'm gonna do. I know it's a bit confusing, but then if you draw it out in a piece of pen and paper, it becomes simple. It's difficult for me to explain using Excalidraw. So equals new int n, right? So dpi plus 1 is actually next, dpi plus 1 is next, right? This is actually the current row's value, and once the entire row is calculated, this current row, right, it becomes the next for the next iteration. And then next of 0 will actually store the answer, because as you can see, right here, this loop ends when the value is -1, right? And then at that moment, the next will actually hold the final answer, right? The first index of the next array. So hopefully this also runs. Yes. Let me show you, right? This is the code. So I don't need all of this. I can just remove this and become so much cleaner, right? This is the simple code. I can just submit this and we are good to go. Yeah, so the space optimized solution is also done, right? Now we have managed to improve the space complexity from n into n, because if we're using a single next array, 2 arrays actually, but one's a temporary array, so it's big O of n. And I know this, I don't think I've managed to explain this problem quite so well, but then the code that I've written is absolutely clean, right? This is how you should write a space optimized code in dynamic programming, right? It's really clean, right? If you compare this to the first solution that we did, let's go back here. You can see, right, we needed to check some conditions and then use these values, right? But then compare that to the current solution, right? We didn't even need to use an m into n array. We could just use a single array and just 2 loops, right? So there's no recursion stack, there is no extra n into n array, right? We could just use a single n size array and just 2 for loops and no recursion stack, and our problem is solved. Hey, Dhue Jivrajani, how are you, man? I didn't think anyone would be joining this stream, but then, yeah, welcome to the stream if you're still here. I'm going to be ending the stream now. This is the problem that we were solving, right? Given a triangle, return the minimum path sum from the top to the bottom. And we have done all 3 solutions. We have done the basic recursive solution, we have done the memoization solution, right? We have also done the tabulation solution, and we have also space optimized it, right? So yeah, hopefully someone got to learn something new today, and hopefully I can explain dynamic programming solutions in a better way the next time. So yeah, that's all for today. Thank you for joining, and I'll see you in the next video.